Good morning, student. Namaskaram. Today we are going to discuss one topic from 12th physics, chapter name nuclei, topic name mass defect. Okay, so this is one of the important, fascinating concept in nuclear physics, which is mass defect, and the next topic is binding energy, which is both topic, which is very important, fascinating concept in the nuclear physics. These ideas like binding energy and mass defects are crucial for understanding the stability of an atomic nuclei. Okay, stability of atomic nuclei and binding energy, that is energy released in nuclear reactions. Okay, right. So by the end of this class, you will able to define what is mass defect and what is binding energy, and how the binding energy per nucleon varies with mass number, and understand the significance of these concepts. Okay, okay, let's dive in. First of all, mass defects. So definition, that is, when we study the atomic nuclei, we notice something interesting. That is mass of nucleus. Okay, in atomic nuclei, we notice something interesting. That is, the mass of the nucleus is always less than the sum of the masses of, if its individual protons and neutrons. Okay, because in nuclei of the atom, there are two particles, that is elementary particles. That is, one is proton, another one is neutron. Proton is a positive charge, neutron is a neutral charge. Okay, got it? Okay, so there is a difference in mass. You can see that the mass of the nucleus is something, okay, which is less than the sum of the masses of individual protons. Already you know that nucleus is made up of protons and neutrons. But in terms of mass, there is a difference in mass. This difference in mass is called mass defects. Okay? This difference in mass is called mass defects. Okay? Let me repeat this. That is mass defects. Mass defect is the difference between actual mass of an atom, okay, and sum of the masses of its protons, neutrons, and electrons. Clear? Okay. So, for example, in terms of atom or in terms of nuclei, always there is a mass difference. Okay. Right. For example, mass of a helium atom. Already you know that, and you can get it from the internet. That is, mass of the helium atom is 4.00260 AMU, atomic mass unit, which is a unit for mass of that atom. Okay, but the components of that atoms, mass of its components, but mass of its components is Just 4 point for the helium atom, okay? Just 4.03298 AMU. You can see that there is a difference, which is 4.03298, but which is only 4.00260 AMU. So the difference in the mass, difference in these values is mass defect. Some concept of mass defect. Okay. So this is a atom. Here nucleus. So two proton, two neutron, and the two electrons revolve around the nucleus. Okay. So the mass is for helium atom. Okay. This is helium atom. So mass 4.00260 AMU. This is the mass of this atom. Okay. And its components like two proton, two electron. So this is electron, this is proton, this is neutron. Okay. And two neutron. Mass of these components is just that is 4.03298 AMU. So the missing mass, missing other difference. Okay, the missing mass equals a binding energy. Equal mass, that is equals a binding energy of the holding the atom together. Okay, this is a mass defect. For example, you can write more and many number of examples for this. Like so, for example, I can give another example for this mass defects. For example, first of all, mass defect equations. So already you know that that is a missing mass. Okay, so mathematically mass defect defined as del m. This is a mass defect. So which is equivalent to sum of masses of protons and neutrons minus mass of the nucleus. Okay, this is a general formula. So del m is equal to sum of masses of protons means ZME. Sum of the neutron mass, okay, so NMP. I'm sorry, MN, okay, NMN. Total mass means capital M. This is the formula of mass defects. Okay, so MP means mass of the proton, MN means mass of the neutron, Z means atomic number, N means how many neutrons are there. Okay, so for one mass for one neutron, there will be a one mass. For 100 neutrons, 100 into that mass. Yeah, so that's why we will write like this: is there MB plus NMN minus M. This is the total mass of the nucleus. So that is experimentally found that the mass of any nucleus is always less than the sum of the masses of individual constitutional particles. Clear? For example, I can give another one example for this because which is very interesting. For example, iron 56. Okay. So iron 56 contains 60 to 26 protons, 26 electrons, 30 neutrons. Because already you know that is 56. Okay. So this is a chemical element ferrous iron. Okay. 56, 26. So 26 protons, 56 minus 26, 30. So 30 neutrons and 26 electron because of number of protons is same as number of electrons. Okay. Right. The experimental atomic mass of this ion, that is 55.9349 AMU. This is the experimental mass of that atomic mass of that ion. Okay. Now mass defects. Mass defect. So atomic number is, this is 26. This is atomic number 26 into mass of protons. Okay. Mass of protons plus N, M, N. Yeah. N means number of neutrons. So here 30 neutrons. So 30 neutrons. M, N, M, N. That is mass of the neutron. Yeah. Mass of neutrons. Minus total mass. That is atomic mass. Okay. So already we have a atomic mass value. So 56 point. But we have to substitute the mass of the protons here and the mass of the neutrons here. So okay. Okay. So now I will write this equation like this. You can see that is mass defect del m 26 mass of protons, that is one mass. Okay, so one proton's mass, that is 1.00785 AMU. Okay, this is the mass of the protons and mass of the neutrons. So 30 mass of the neutrons 1.0086665 AMU minus atomic mass. Already you know that 55.9349. Okay, right. So multiply this and subtract this amount. First of all, multiply 26 into 1.00785. So 26.20345. Okay. And multiply this 30 into 1.0086665. So 30.25995 minus this is. So add those value. 26.20345 and 30.25995. Okay. So which gives 56.4634. Okay. Minus 55. 9349. So subtract that this true value. So you will get that is 0.5285. Yeah, correct. So which is delta. So this is the mass defect in this ion element. Okay. So mass of the ion, which is 58.93. Okay, but its components like protons, neutrons, that both mass, which gives 56.4. So there will be a something different. Okay. So where has this mass disappeared? Where this mass goes? Yeah. So you have now one question. Why mass defect in this element or in any element? Okay. Why? Or what is the reason behind that? Where does where does this missing mass go? Yeah. Okay. So according to Einstein famous equation, already you know you have familiar with that. That is E is equal to mc square. Mass can be converted into energy. This is a simple concept behind this equation. That is E is equal to mc square means mass can be converted into energy. The energy which depends mainly on the mass and speed of light. Okay, right. So mass defects, according to Einstein, this mass defect converted into energy. That energy is called as binding energy. What is the use of this energy, sir? Yeah, already you know that that term binding energy. But what is the use? Binding energy which holds the nucleus together, because in nucleus proton is there, neutron is there, and electrons revolve around the nucleus. Okay, but the proton positive charge, so repel each other. Neutron is nothing but which is a neutral charge, so there is no impact by the neutrons. But anyway, around the nucleus, there is a electron. So there is a attraction between the protons and the electrons also. But so this is a atomic structure. In atomic structure, we know that from that concept of Bohr's, Niels Bohr, etc., concept. Okay, right. But here the mass defect actually converted binding energy, which holds the nucleus together. Okay, right? Okay. Then we will go into that next topic, binding energy. Binding energy. Binding energy is the energy required to break apart a nucleus into its individual protons and neutrons. Okay. So this is a concept of binding energy. So binding energy is the energy required to break the nucleus. Okay. Break the nucleus apart into its constituent protons and neutrons. Is it correct? Okay. So it is also that energy released. Energy released when a nucleus is formed from its constituent particles. Okay, you can say that anything. So energy required to break the nucleus into individual protons or nucleus, or energy released when a nucleus is formed from constituent particles. So this is a binding energy. Binding means you know that holding. Yeah. So that nucleus holding the positive charge protons and a neutral charge. Okay. So this is a binding energy. Okay. So now let's dive into the equations. Equations. Binding energy. Okay. So binding energy, which may be denoted as EB. Okay. So which is nothing but mass defect into C square. Yeah. Very simple. Binding energy is directly related to the mass defect through the Einstein equations. So here, this is a binding energy. So B dot E means binding energy. This is mass defect. This is speed of light. Okay. So greater the binding energy means more stable the nucleus. Greater the binding energy, the more stable the nucleus. Clear? So again, I'm repeating that concept. Mass defect, already you know that. So Einstein um, provided the important famous equation, that is E is equal to mc square. According to that relation, the mass can be converted to energy, and the energy can be converted into mass also. Okay, so reverse case is also true. So like in the case of iron 56, so it is made up of, already you know that 26 20 to 26 30. Okay, so that has mass difference. That mass converted into energy. Okay, right? The energy is called binding energy. So which is equal to del m dot c square. So in fact, to separate that, like for the example, carbon 12 or ferrous 56, yeah, whatever else. Okay. In fact, to separate that ferrous 56 nucleus into its individual constitution, we must apply the energy equal to the binding energy of the nucleus. You provide some energy to break that nucleus, but that energy should be equal to binding energy of that nucleus. Okay, now you clear with that concept. Clear? Okay, again, you can see that the relation between the binding energy and mass effect. It also can written as like binding energy, which is equal to mass effect. Already you know that mass effect, which is Z mp plus n mn minus total mass. This is the equation for mass defect into C square. This is binding energy. Okay. Okay. You know that what is Z and what is N and what is M, what is C, and what is binding energy. Okay. Next, we will move into that next topic. Binding energy per nucleon. So binding energy per nucleon. This is next concept. Now let's talk about binding energy per nucleon. So this is a binding energy divided by the total number of nucleons. Okay. So binding energy per nucleon means per means divided. Okay. So binding energy divided by the total number of nucleons. What do you mean by nucleons? Already you know that nucleons is nothing but which is the combination of protons and neutrons. Protons plus neutrons is called as nucleons. Okay. So divided by the total number of nucleus in that nucleus. Clear? Okay. So it tells us how tightly each nucleon is bound in the nucleus. So binding energy per nucleon tells that how tightly each nucleon is bound in the nucleus. Okay, right. So mathematically, we can write this binding energy per nucleons like that. Binding energy per nucleon. All right, that already you know that binding energy you can write E B subscript B or B dot E. Okay. So per nucleons, protons per neutrons. So protons per neutrons, which is nothing but atomic number, mass number. Yeah. So mass number. This is mass number. A is mass number. Okay. So because the number of protons and plus the number of neutrons, which is denoted as, which is called as mass number of that nucleus. Yeah. So A is nothing but mass number. That is a total number of that nucleons. So this is binding energy per nucleon. How does it vary with mass number? You know that binding energy per nucleon, which is depends on EB by A. Okay. So binding energy depends on that mass number. Okay. But how does it vary with mass number? So for example, take that light nuclei. Take one light nuclei, which has a small mass number. So small a. Okay. Binding energy per nucleon or A. Okay. So binding energy per nucleon increases rapidly with mass number. Yeah. Because from equation, you know that suppose A increases, binding energy decreases because both are reciprocal quantity. Binding energy reciprocal to 1 by A or inversely proportional to the mass number. So mass number increases, binding energy decreases. Mass number decreases, binding energy increases. So that's why I'm saying that is binding energy per nucleon increases rapidly with the mass number because small a means high binding energy or increasing binding energy. Right? Right. Then, so mass number increases in the periodic table. Already you know that. Okay. So increases. So binding energy decreases. So it reaches a peak around. Peak around at A is equal to 56. Already you know that A is equal to 56 for ion, which is the most stable nucleus. Okay, which is the most stable nucleus. So atomic number increases, binding energy decreases, but it reaches a peak value around A is equal to 56. That A means mass number. Mass number 56 for what? Ion. Okay. So which is the most stable nucleus? For heavier nuclei. So heavier nuclei means which is greater than the atomic number 56. Sorry, mass number. Okay. Which is greater than the mass number uh, greater than the 56. Okay. So for heavier nuclei means here mass number A which is greater than 56. So A increases, binding energy decreases. Yeah. So the binding energy per nucleon gradually decreases. Okay. So the binding energy per nucleon gradually decreases for the mass number greater than 56. That's why mass number 56 that is for ion which is most stable, but greater than the 56 elements which is unstable nucleus. Okay, because binding energy decreases, so the holding energy less, so it decays. Okay, clear? So from this concept you know that so the nuclei near ion are the most stable, while lighter and heavier nuclei are less stable. Clear? Okay, right. Okay, now, so what is the significance of this binding energy per nucleon? What are the some significance of this binding energy per nucleon? Yes. Okay. So binding energy per nucleon has profound implications. For example, nuclear stability. Nuclear stability. Nuclear with high binding energy per nucleon are most stable. That's why ion is considered the most stable element. Yeah. So high binding energy per nucleon, most stable. Most stable. Okay. So that's why ion considered the most stable element. Second one, in nuclear reactions. In nuclear reactions, light nuclei combine with heavier nuclei, heavier nuclei, okay, release energy because the product nuclei energy, that is product nuclei, have higher binding energy per nucleon. Okay, so light nuclei plus heavier nuclei, it forms one nuclei. Okay, which has higher binding energy per nucleon. So it may be used. Okay, right. In nuclear fission, so this is like a nuclear fusion. In nuclear fusion, fusion means coming. So light nuclear, heavy nuclear. In nuclear fission, heavier nuclear fission, heavier nuclei or heavy nuclei split into two light nuclei, two or more light, or two smaller nuclei, three smaller nuclei. Okay, so light nuclei, light nuclei. So again, the energy released here because smaller nuclei have higher binding energy per nucleon. Yeah, already I told you that smaller nuclei have higher binding energy. Heavier nuclei have less kind of binding energy. So in nuclear reactions, in nuclear reactions, there is a types of two types of reactions, that is fusion and fission. So binding energy per nucleon have impact on this concept, nuclear stability, nuclear reactions. Okay, next, energy production. Energy production. The sun, around, and stars generate energy. Yeah, already you know that sun, star generate energy through fusion. Yes. So fusion means coming. So converting hydrogen into helium and releasing vast uh, amount of energy. Okay. So hydrogen into helium and releasing vast that is vast amount of energy is released during that reactions. That is called as energy production. In nuclear plants also, fission reaction between that nuclei. So between that, according to the nuclear power plants concept, it may be uranium or plutonium. Yeah, which is used to produce energy. So that's in that concept also binding energy per nucleon used. Understanding the universe, which is also in one application for this understanding the universe. So binding energy curve explains. I will draw a binding energy curve later. Okay. So the binding energy curve explains why certain elements are more abundant in nature or abundant in the universe. Okay. And why nuclear reactions? Reactions release energy. So understanding the concept of binding energy per nucleon have uh, a lot of profound implications. Some of the implications, you know, familiar with it. So, in understanding the universe, the binding energy curve explain why certain elements are more abundant in universe and why nuclear reactions release energy. Because all the concept which is belongs to that binding energy per nucleon. Okay. So, binding energy curve means so you take that. Okay. Thanks. So binding energy curve, like for example, here number of nucleons, that is A, mass number. Here binding energy per nucleon. This is y-axis, this is x-axis. This is in million electron volt. This is mass number. Okay. For hydrogen, helium, like that, that graph shows like this. Wait. So here, 0, 0. So 50, 100, 150, 200, 250. Okay. Here 1, 2, 3, 4, 5, 6, 7, 8. Like that. Okay. So for a hydrogen atom, it is H21. Yeah. So graph start here. For helium atom, helium 3, 2. So goes like that. And this is a rough graph. Okay. So this graph goes like that. So here helium 4, 2. So and then it will goes down and increases and goes down and increases. So that graph goes like that. So this is a maximum position. So in that position, that element ferrous is there. Yeah, ferrous 56, 26. So here uranium is there. Uranium 238, 92, which is the most unstable nucleus. Uranium 238 always decay into that components like plutonium, uranium 235, because most unstable elements, that is uranium 238 is there. Strontium like that for strontium, plutonium, gold. So on the graph also. So this is a binding energy curve. So binding energy per nucleons means binding energy is nothing but mass defect into C square per nucleon is by mass number. So average binding energy per nucleon is the energy required to separate the nucleon from the particular nucleus. Binding energy curve means the binding energy is plotted against the A of all known nuclei. We get the binding energy average curve here. Okay. Clear? So this is a binding energy curve. Okay, right. So summarize, to summarize, mass defects and binding energy are the fundamental concept in nuclear physics. The mass defect explains the missing mass in the nucleus, which is converted into binding energy. The binding energy per nucleon varies with mass number. Yeah, peaking at ion and decreasing for lighter and heavier nuclei. So, which peak at only at ion, and it has a value with the decreases compared to the ion, both for lighter and heavier nuclei. So this variation is the key to understanding the nuclear stability, energy production, and that process that power the stars and the nuclear reactor. Okay. So I hope you this class has given you a clear understanding of this concept. Okay. So if you have any questions, feel free to ask me. Any questions? In next class, I will teach you that radioactivity and law of radiative decay. Okay, you can unmute yourself and ask me any question regarding this concept. Please unmute KGBV Satan Pali. Please unmute and ask me any doubt regarding to that mass defects, binding energy per nucleon. Is any, do you have any doubts? Do you have any doubt? Okay. So let me explain with one example for this concept, binding energy per nucleon. Okay. So for helium 4, 2 nucleus, binding energy per nucleon, binding energy per nucleon is, we know that binding energy of helium 4 to binding energy. So mass defects, already I told you that is for helium. Already I was give that mass defect value. Okay, just multiply it with the c square. Okay, so for example, in helium there two neutron, two proton, two electron, mass number, atomic number also. Okay, so mass defects to Z mp plus n mn minus m. So this is mass defect. With the c square, it becomes as binding energy. So put that value, you will get binding energy 28.33 million electron volt. So binding energy per nucleons means 28.33 million electron volt by A. So here this is a A. So divided by 4. So 28.33 divided by 4, which gives approximately 7. So you need million. So this is a binding energy per nucleon for the helium nucleus. Okay. So for the helium nucleus, 2 proton, 2 electron, and 2 neutron. So put those values of the masses of protons and neutrons and total mass there, and into c square, you will get binding energy, again divide that binding energy with the mass number, you will get binding energy per nucleon. Okay, so this is one simple example for this concept. Okay, so today class is over. I will explain another concept in next class. Okay, thank you. Jai Bharat, Jai Hind, Jai Vidyashakti.